Morning, everyone. Does Dr. Nasser use like the wide slides on foundations? Was he mad that I adjusted the projector yesterday? No, it was good. Are you in the class here like all morning, pretty much? It's this and then foundations and then something and then transportation? Yeah. Was anybody mad about the projector? Perfect. I'll leave it then, because I remember the IT guys were getting kind of pissed at me last year for always doing that, and there was one person who was always getting mad about it. That's beside the point. We're back in CE 3063 now, structural steel design mindset. And just to remind everybody of our adventure throughout the term this fall, I'm putting the course map back up here. We're going to spend between now and lecture 10 actually, talking about steel structures in general, structural shapes. I'm going to talk about how buildings work, what the role of bracing and different framing is in structures. We're going to spend 4 or 5 lectures, I can't remember the exact amount, on calculating loads on buildings in accordance with the building code. And then I'll talk about the probabilistic tools that we use to make sure that structures are safe for the public to use. And these things are going to be embedded in the building code and the steel standard that we're using. We don't have to think about the statistics as often when we're actually applying this in practice, but I want to give you a little bit of a background on the statistical framework behind what it is that we're doing. Today, though, we're going to just start by talking about structural steel shapes and properties, the kinds of things that we use to actually build structures using structural steel framing. The other day, I had introduced this less optimistic, perhaps, definition of structural engineering, where we have it's the art of molding materials we don't really understand into shapes we cannot really analyze, blah, blah, blah. Today, we're going to be focusing on the molding materials we don't really understand part into shapes that we can't really analyze part. Okay, so today is basically an introduction to structural steel. I'm going to talk about some of the shapes. I'm going to talk about grades. I'm going to talk about the variability in the strength of steel. That's going to be an important aspect, especially when we come back to designing for safety, when we're considering our ultimate limit states. If you want to get more details, I'm not going to go and, I can't read you guys a textbook on this stuff in lecture, but if you go to the recommended course text, which is useful sometimes, you don't need it, but if you want it for background information, you can read chapter 2 of that. But the CISC handbook, part 6, is pretty much all about structural steel shapes and grades, and you can get a lot of information there if you want to go read that up after going through lecture this morning. Basically, after this, you should be able to identify some common structural steel shapes and some of their common applications. For example, you'll be able to tell me after today what we typically use a wide flange section for. You should be able to discuss steel grades and select appropriate material properties for a given grade. And more important from a theoretical standpoint, less important from a practical standpoint, you should be able to describe the bias and variability, which are terms I'll introduce today, and the properties of structural steel shapes. Does anyone have any questions about the menu for this morning and what we might be embarking on today before we get into the material? Good. Structural steel is basically formed, for the most part, by hot rolling. Has anyone heard of hot rolling or cold rolling, or know what cold forming might be? Any one of those terms? Anyone know what hot rolling is versus cold forming? That's okay. Basically, steel is a molten material. It gets mixed together in liquid form. They melt down a combination of iron, carbon, magnesium, probably other chemicals that you learn about in material science, right? You had that phase diagram and you learned about different types of steels in material science with Dr. Rogers, I believe. And so basically, once they get all that liquid and all those ingredients into a pot, they boil it down. They let it get to a molten steel temperature where they can basically take a molten rectangle and they will roll it through a series of rollers to make a bunch of different kinds of shapes. In this form, steel is highly malleable. So while it's malleable, they roll it into shapes, they let it cool off, and we have our final structural form. You can roll shapes in a bunch of different configurations. The most simple would be a square bar. So it's just a square rod, basically. Round bars, flat bars, and plates. Those are the most common shapes for the most part and the simplest. For example, this is a flat bar. The difference between a flat bar and a plate typically is that a flat bar has an aspect ratio of about 1 to 10. And when you get more than 1 to 20, roughly speaking, you start to get into the flat plate kind of situation. So I'm going to pass this around. Just notice how heavy it is. I don't know. Wouldn't think that this would be particularly heavy when you first pick it up, but it's heavier than you might think it is. So those are some common basic shapes. For the most part, we don't use square bar or round bar too often in structural applications. Round bars you might see as like a very light bracing. Anyone go to Costco? If you go to Costco, you've seen round bar braces. As soon as you walk in, you see round bar braces everywhere in the ceiling and the walls. So that's often used for a very simple kind of bracing. Flat bar is often used for some kind of bracing applications. It's also used to make connections, and plate is also used to be cut out in custom shapes to use to connect these pieces together. We also have different kinds of structural shapes. I'm sure everyone has seen this before. You've probably called this an I-beam in the past. We don't call them I-beams as structural engineers. If someone says I-beam, you usually don't, right away they're not a structural engineer. We call them wide-flange shapes, or sometimes H-piles. Geotechnical engineers will usually call them H-piles because if they're shorter and wider, they use them as piles. If they're wider and deeper, we tend to use them as beams or wide-flange sections. We can cut these down into WT shapes, and so literally a WT is just made by taking an I shape that's rolled from molten steel and cutting it in half. And then we've got a few others as well. Channel shapes, angles. These ones are all hot rolled for the most part. You can make angles by taking a piece of plate and just bending it. That's called cold forming into a bent angle. These other shapes, square HSS and round HSS, the preliminary form is actually a plate. So they'll hot roll a plate, and then they will bend it twice to make a square, or bend it in the radius to make a circle, and then they'll weld the seam together to close the shape. Okay, so that's how they make those. Pretty common for columns and braces because they have pretty uniform properties about both axes, and there's a lot of steel far away from the center of the section. So when you see these, and you're going to be looking at these quite a bit in this course, wide flange sections, we designate them as W, that's the shape, and then a number times a number. And basically what the number is some kind of nominal depth in millimeters. So if I was to say you've got a W200, that means it's about 200 millimeters tall, which is about 8 inches or so. And then if you've got a W410, that's about 14 or 16 inches tall. And the second number is the mass. Okay, so one of the things that we're going to talk about quite a bit in this course, or not quite a bit, we're going to talk about it at least once, is the difference between shapes that are typically used as columns and shapes that are typically used as beams. Which of these two shapes, left or right, or what would I say? The right hand, all right? The right hand shape here, the W410 by 46, it has the same amount of steel as the W200 by 46. Would you use a 410 by 46, do you think, more often as a beam or as a column? Any idea? I hear some weak beams. Who said beam? You can all raise your hand. Beam's the right answer. Why would you use it as a beam and not a column, do you think? Well, it's really deep, right? Beams are stronger when they're deep. They're stiffer when they're deep. The moment of inertia goes up. And some other properties like the plastic section and elastic section moduli that we'll talk about later on in the course are also bigger, which increases the bending strength. So the shapes on the left tend to be used as columns. The shapes on the right here tend to be used as beams. There's the same amount of steel in them, but they tend to have specific applications. Angles. Sometimes you have equal leg angles, which means the two legs are the same. Sometimes you have unequal leg angles. Basically how they're designated is the shape L, that's pretty convenient, with a number times a number times a number. And usually they're just lengths. So the long leg will come first, the short leg will come second, and then the thickness. That looks kind of weird to me. I don't know if it looks weird to you. You might think, well, 152 by 102, why isn't that not just 150 by 100? That would be a round number in millimeters. We're a metric world. Why do you think that those numbers are so weird? The Americans, well, more specifically, the world before metric in general. We are still more or less, very closely tied to the economy in the United States. And the steel suppliers in general, even in Canada, before we introduced metric, they were set up to roll things in imperial measurements. What do you think 152 millimeters corresponds to as a measurement in imperial? Any idea? That's a 152 by 152 by 13. Any guesses? That might be a 5, actually. It is 6 inches, right? So 6 times 25.4 gives about 152 by 4 by something that's like a bit more than 5/8. What's 11/16 roughly? Okay, so we don't have to care about that. We just have to know that that's why these numbers are a little bit weird. We deal with these things in terms of our metric equivalents, but we still very much live in an imperial world from a fabrication standpoint. So that is an equal leg angle. I think it's 5 by 5 by ½ inch, or about 127 by 127 by 13. Then we've got our hollow structural shapes, and we've got squares and circles. Architects love these because wide flange shapes, angles, they look kind of ugly, or at least architects think they look ugly. Closed shapes make it look like it might even be a piece of timber. Architects love timber. So anything that's closed off, you can't see all these kind of plates sticking off. Architects tend to love these. We've got square or rectangle, and usually they're designated by HSS, which means hollow structural shape. We've got 152 by 102 by 11, which would be a 6 by 4, depth by width, with about a 11/16 thickness, 11 millimeters thick. Basically, one thing to know here, and I don't have it specifically here, but there's also a radius of curvature here. Whenever you bend steel, you can't have no radius. The radius of curvature when you bend a piece of steel is generally going to be equal to the thickness of the wall that you're bending. And so when I pass this around, you're going to see this is about a ½ inch thick. And if you tried to measure the radius of the inside corner, it's also about 1/2 of an inch thick. We've got circles, same thing, but it's just diameter times thickness. And circles tend to be used a bit more in architectural applications than an HSS might be. HSS tend to be used as columns or braces, and then they end up getting tossed inside a wall so nobody can see them. How do these things come together to make certain forms and shapes? Well, in this case, we've got a picture of a bracing beam and column arrangement in that school that I showed you the other day. We've got a square HSS column. I believe that these would be 200 by 200 by something, 8 by 8 or so, maybe 10 by 10. We've got a wide flange section as the beam that's getting connected to the HSS using a flat bar connection. They're all bolted together using different bolts. We've got a flat plate that got custom shaped or cut out using a laser to make this gusset plate connection. And then we've got a flat bar brace coming in to connect to that gusset plate. Okay. Oftentimes we bolt things together, but we can also weld them together. Here's a smaller structural bolt. I think that's 3/4 of an inch, so it might be 7/8. So oftentimes we'll bolt things. It's pretty easy to do that in the field. Other times we'll weld them. And so here's a couple of flat bars that are welded together. We'll talk more about welds and bolts later on in the course, but those are a couple ways that you can make these kinds of connections. Here's another view of a different part of the same structure. Same HSS column, but now we've got a series of angles involved now. On this connection here, for example, of the beam to the HSS, we actually have a series of angles. The angles are a little bit longer. They're welded to the HSS column, and then the wide flange section gets bolted to those angles to transfer the vertical load from the beam into the column. And you can also see that there are some angles here to make the connection of the bottom chord of this joist. This would be called an open web steel joist. Here, you've got angles as well, but you can tell by the fact that the corners are rounded, those are bent plates that are formed into angles. That question?
This might be a stupid question, but is there any reason for some of it to be rough steel that's not powder coated and the rest of the steel to be powder coated?
Yeah, that's a good observation. So this is actually primed. So this is a primer.
Okay.
And this is unprimed or bare steel. Usually if you're going to paint it and expose it, you'll prime it so that the painters can come in and paint it. Steel that has a little bit of rough surface corrosion on it It's actually good for the steel because it protects it from deeper corrosion. That's usually going to get buried in a wall or in a floor, and you're never going to see it again. And so that often just gets left unfinished because it's cheaper to do that.
So that part must be going to like the gymnasium or the cafeteria, something like that.
Exactly.
Okay.
Yeah. Was there another hand that I saw? Yep.
Back in a couple slides ago, you said something about common grade. I'm confused what grade means.
We're going to talk about that momentarily. Yep. So those are some typical applications, wide flange sections, HSS angles. We'll talk about those in more detail throughout the course, and we'll talk about how to design them. Obviously, that's the focus of the course. Some other shapes that get used time to time. Here's a steel channel. It's called a channel because it's kind of makes a C shape. It's designated with the shape C. Again, very similar to wide flange sections, nominal depth by mass in kilograms per meter. They often get used for staircases. And so actually, if you go to the stairs just out here, you'll see that the stairs are actually a channel that have some timber, light wood finishing just to make it look a little bit nicer. They tend to be used as stairs quite often because these little pieces of steel provide some strength, but the flat face on the left-hand side here makes it easy to connect stair treads into the side, which makes it easy to put these staircases together. WTs almost always are used as some kind of brace. Okay, so usually they'd be a diagonal brace. They might form the chord of a truss, but generally speaking, you take the measurements of an equivalent wide flange section and you cut them in half, and that's how you get a WT, right? So a W410 by 46 gets cut in half to make a WT 205 by 23, right? These are just the same properties, but divided by 2. And if we looked at the 200 by 46 versus the 410 by 46, if we cut those into structural T's, we get a 100 by 23 or a 205 by 23. Which of these two do you think would better serve as a brace in the building? Any ideas? We'll talk about that as we go out through the course. Generally speaking, you want to get the shapes that are wider and less tall to use as braces, because usually with these WTs, we're going to bolt them by the flange here to the gusset plate connection. And the shorter and wider it is, the more steel we have in the flange, which means we're going to make more effective use of the steel in the cross section if we have a shape like that. I realize now that I didn't necessarily define some of these terms, so when we have a wide flange section, the flanges are the top and bottom pieces here, right? It's wide flange because the flange is wide. The web is the piece that connects those two flanges together. And then basically everything else is legs or walls of an HSS section. And one last point I'll make about hot rolled shapes, and I'm going to focus on wide flange shapes because we're going to come back to this later on when we talk about compression and bending of steel shapes. When we do the hot rolling procedure, it's very hot, right? Like hundreds of degrees Celsius when it comes out of the rollers. As that cools down from hundreds of degrees Celsius to tens of degrees Celsius, different parts of the section are going to cool at different rates. Generally, the pieces that are further away from the center of mass of the structure are going to cool sooner. So the tips of the flange are often going to cool first, which means that they're going to solidify. And then the web tends to cool off slower and solidify later. If you have something that's already solidified, and then you have something that's cooling down and shrinking, the web is actually going to pull the tips of the flange here into compression, and that's going to develop some tensile stress in the web and in the regions where the web connects to the flange. This is called the residual strain or residual stress because it's a stress that's left over after the hot forming process. What do you think about the equilibrium of that stress distribution? If I was to multiply that stress by the area, would I get a force, do you think? Do you see wide flange beams flying around in space ever? No. Things can't move if there's no net force acting on them. If this W beam was just sitting there, wide flange section was just sitting there, it's not moving, that means there's no net force acting on it. That means that the internal stresses have to be self-equilibrating. There's going to be a compressive force that develops from the compressive stresses. There's going to be a tensile force in the web from the tensile stresses. the compression and tension forces will be equal and opposite, which means there's no net force acting on the cross-section. But when we start to apply stress from compression or from bending or from tension, we have to keep the fact that we already have an initial stress state in this cross-section in mind, because if the compressive stress, for example, at the tips of the flange, it tends to range from 30 to 50% of the yield stress. That means we're not going to be able to apply the full force on the cross-section before it starts to yield. It's going to start to yield the tips of the flange earlier, or if we were to pull it into tension, we're going to start to yield the web first because it already has a tensile stress in it. We're going to park that there for now, but just keep this in mind. I'm going to remind you again a bit later when we start talking about the strength of different kinds of members, particularly in compression. Does anyone have any questions about structural steel shapes, kinds of shapes or applications, or what it means to have this residual stress locked into the cross-section of hot-rolled shapes before any loads are actually applied? Any questions? All right. So now we're going to get into material properties, and this is where we're going to start talking about grades of steel. Everyone's seen this curve before, I hope. At least in mechanics of materials, you still do that lab where you pull a coupon apart, right? And you do the stress strain curve, and it doesn't look quite the way you maybe expect it to look. And in material science, I'm sure you talk about it as well. Basically, you would mill a coupon. It might look something like this. It could be a circular rod, or it could just be a flat shape. And you put it in a machine, and you measure the force that you pull with. You measure how much it elongates. And if you know what the area is at the start, then you can measure the effective engineering stress on the cross-section as you pull it apart. Basically, at the start, we're going to have a very stiff elastic response, right? We all know, I hope that we remember, that the elastic modulus of steel is 200,000 megapascals, 200 gigapascals. And as long as it's in the linear range, we can keep our analysis relatively straightforward. When we get to a certain point, though, what often called the yield stress or the strength of the steel, we're going to start to dislocate some of those molecular connections, the crystal structures. And for mild steel with relatively low carbon, we tend to get a pretty well-defined yield plateau where we don't get a change in the stress. The stress is pretty uniform over that region, and we call that the plastic range. And for the most part, we can go from about 0.002, if it's 400 megapascal steel, to 10 times that strain or more in that yield plateau. So we can get a significant amount of deformation, 10 times the yield deformation, without a significant drop or increase in stress. Then we start to get the strain hardening going up to maybe 10 times the plastic range. So basically all I want to really communicate here is there's an important property, Fy, that tells us when we're going to exceed the linear strength limit of the steel. Even after it yields, we tend to never lose a significant amount of strength, even if we stretch the bar by 100 times the yield strain of the structural steel. At a certain point, we will develop a peak force or a peak stress. In this course, we call that Fu, the ultimate tensile strength of the steel, versus Fy, the specified yield strength for the structural steel. Shouldn't be anything new here. Important to identify Fy, Fu, and to highlight the naturally ductile behavior that we get from structural steel when we pull it apart in tension. Something you probably never talked about before, and I don't want to get into a great amount of detail here. In 2023, you probably should talk about failure criteria, but I don't think you do. Have you talked about failure criteria in 2023? Does that ring any bells? It kind of comes from, like, it's if you did more circle and then you did one more unit, which you probably should do in that course, you would learn a little bit about at what points you have, you've got the stress states in 2 dimensions, you've got some shear. Anyway, from that theory of failure of ductile metals, basically the important things to take away here without me going into that theory is that if you were to turn this into shear instead, if you were to load structural steel in pure shear, generally the von Mises failure criterion would indicate that the stress when you start to yield the steel in shear is about Fy over root 3, which basically means the shear yield stress is about 0.577 times Fy or so. And that's going to be important because we're going to see steel beams later on and steel bolts that fail in shear. And so we need to be able to recognize when we're using the tensile strength modified by a factor to account for the fact that we're trying to look at it as a shear strength. Okay, so the only thing you need to take away from this slide is that when something's failing in shear, it's failing at a stress that's about 60% of the tensile strength of the material. The other thing that's important here is the stiffness of the material in shear. Generally, it tends to be about 3 times more flexible when loaded in shear. The slope in the elastic range for shear, G, is about 77,000 megapascals or 77 gigapascals. And when you're loading steel in shear, it tends to be significantly more ductile. We have a bunch of different kinds of shapes. These categories come from a standard called CSA G40 2021. Really not important to go through that standard. There are a bunch of different kinds of steels that might be more useful for different kinds of situations. For example, if you're going to have steel that was exposed in a bridge application, you might want to, and you were going to leave it unpainted, you would use an atmospheric corrosion resistant steel because it's not going to corrode when exposed to high humidity levels. Most of the stuff we're dealing with is in buildings. We're never going to see it, but we're going to want to weld it. 99% of the time, and in practice, 80% of the time, you're just going to be dealing with type W structural steel. It just means you can weld it. There are different chemical compositions that don't weld very well. If you try and heat it up and fuse it together, it's not going to create a very strong weld. So in this class, we're generally going to be focusing on this type W structural steel. A grade of a steel is basically just the category, which in our case is going to be W, and the yield strength, which most commonly is 350. Basically, the most common structural steel on the marketplace, especially in Canada, is 350W. It means that it's a weldable steel, and the tensile strength in yield is about 350 megapascals. For a long time, channels, angles, plate used to be 300W. Manufacturers have generally since changed to make everything 350W. And generally, unless you ask for something special order, you're not going to see a lot of the other kinds of materials. We're starting to go more towards higher strength steels, especially for bridge applications, but 95% of the time, the manufacturers are going to be providing 350W steel. They can make anything you want, but they have to special order it, and your project's going to take forever if you actually ask for some of those. In our case, we're always going to ask for 350W steel if it's a building application and it's going to be something we want to be able to weld. And so in this course, we're really just going to be focusing on 350W. If I told you the steel was 300W, it just means the strength's a little bit different. You use 300 MPa for yield instead of 350, but the grade here is pretty straightforward. The last thing I'll say about shapes and grades is that there are some specific shapes or grades of steel that we get in Canada for structural steel projects. In Canada, we exclusively roll channels, angles, and bar stock or plates. We don't make wide flange sections in Canada, which by definition means we don't make WT because WT come from wide flange sections. We don't make these S shapes, which just stands for sloped flange. And sometimes we make HSS, but sometimes we don't. Almost every channel, angle, and piece of bar or plate that you're going to have on your project will be from Canada, and it will be rolled to G40 2021 350W. And what that tells you as the design engineer is that you should be designing with these strengths in mind. You've got 350 MPa as a yield, 450 MPa as an ultimate tensile strength. We always import. We do not make these here. It might change with the recent economic pressures from down south, but currently we do not make any of these shapes in Canada. No wide flange, no WT, no S shapes. For that reason, we import them almost all from the US, but not always. But the US has a specific grade for these types of shapes, and that's ASTM, American Standards for Testing and Materials, A992 grade 50. And whenever we have grade 50 steel, we're going to use similar but very slightly different strength properties. Where do you think this 345 comes from? Like 350 is 350 MPa, we call it 350W steel. We've got 345 MPa, why wouldn't we call it grade 345? Similar answers to before, why the shapes have kind of weird length designations, 152 by 102. What was that all about? I can't see who's saying that because it's quiet, but yeah? Yeah, so the American equivalent, roughly speaking, this 50 means 50 KSI, which is kips per square inch. Kips is already a really weird unit because it's kilopounds, which is like metric imperial, so it's kind of a strange unit. But it's a strength or a stress in kips, which is thousands of pounds per square inch. And if we were to convert 50 KSI to MPa, it's about 345 MPa. Now, in more recent years, they've been trying to also get what's called dual certification to also call this 350W, just because. But generally speaking, what you're going to see in the handbooks, whenever you're dealing with grade 50, your strength's going to be 5 megapascals lower than we otherwise would for 350W steel. HSS are a little bit different. We import a lot of American grade HSS, specifically a shape called ASTM A500 grade C. C stands for cold formed more often than not, which means they take hot rolled plate and they bend it and they weld the seam and they don't do anything else to it. Sometimes you can get class H in Canada, which means they hot roll it, cold form it, weld it, and then they anneal it. Does anyone remember what annealing is? Talked about it in material science. Anyone remember the annealing process and what that does to steels or metals?
Is that when you bring a steel or a metal to the heated temperature to relieve the stress, and then you allow it to cool off slowly?
That's right. So the hot plate will cool quickly. They'll roll it, they'll weld it, they'll heat it back up, and then cool it very slowly. When you hot work and weld the seam, you introduce a different kind of residual stress in the cross section. The welding heats up the seam, that pulls things together. And so if you want to get rid of that, you can anneal it and get rid of that initial stress state and also make it a bit more ductile. So sometimes you'll see G40, 20/21, 350W Class H, HSS, or Class C. It's the difference between not being annealed and being annealed. Most of the time, though, for design purposes, because we never really know where they're going to get the structural steel from. You can specify it as the engineer. You can say, I want G40, 20, 21, 350W Class H, HSS. That's your purview. The supplier is probably going to come back and be like, well, you know, if we want this, we're going to have to wait 4 months. This ASTM A500 grade C is available now. Can we just use that? And so most of the time, you're going to be wanting to make sure that they can use this grade C A500 structural steel. And the big thing to look out for here is that the standard ASTM A500 has a higher tolerance on wall thicknesses. So they basically say ASTM A500 has to be 1/2 inch wall thickness plus or minus 10%. What do you think the fabricators are going to do if they're going to try and sell you structural steel?
They're going to get as close to that 10% as they can.
They're going to get as thin as possible while staying at the minus 10% range. They can roll the plus or minus 0.2%, and we'll see that in a second. So they can roll very, very, very tight tolerance. They're going to say, well, we're going to cut 10% off. We're going to save 10% of the steel. We're going to sell it to you for the same price, and no one's going to be the wiser. The engineers know that already a little bit, and so whenever you're designing with A500 HSS, we are going to account for a reduction in the wall thickness of 10%. That's going to be baked into a lot of the properties that we have in the handbook already. So when in doubt, if the grade is not specified, or if you don't have control over the grade, it's always better to assume that you're going to have A500 steel because it's always going to be a little bit thinner for about the same strength. Okay, does anyone have any questions about what it means to be 350W versus A992 grade 50, where we tend to get these kinds of shapes, and what things to look out for as the engineer if you're trying to use any of these shapes on a structural steel project? Excellent. Last item on the menu, we're going to talk about these terms bias and variability in the strength of structural steel components. And basically what this is going to come down to is we don't know with certainty what the strength is going to be. We can calculate something, and we'll do that in a minute, but it might be different, and we'll talk about why. For example, let's just say we had angles that are 127 by 76 by 6.4, that's 5 by 3 by 1/4 inch, It's common to use 2 of these. You can just slap them on a plate, bolt them, and they're used in members of trusses or in braces for brace frames in buildings. If you were in CE 2023 again, how would you calculate the strength of this cross-section in tension? What equation would you use to figure out how strong you expect this set of 2 angles to be before it starts to yield in tension? It's 350W steel, has a cross-sectional area of 2,500 millimeters squared. What do we do here? Do we take a certain number and multiply it by another one, maybe? I can stand here for a couple minutes before someone says it. Someone's got to know how to calculate the yield strength of something in tension, right? Okay, I'll hold your hand then a little bit. We've got a cross-sectional area. It can yield at a stress of 350 megapascals because we've got 350W steel. If we multiply the area by the yield strength, that tells us how. Do you do that in 2023? Please tell me you do that in 2023. You have a truss and you figure out how much force is on it and you're like, what's the factor of safety for, yeah, I see some head nods and some head shakes. Basically, we just take we're going to just use R as resistance. The resistance of this section to yielding would be the area times the yield strength. So we might say that we could apply 875 kilonewtons in tension, which means in and out of the page. If this is a long set of double angles, it's going to take 875 kilonewtons to start to yield this angle in tension. Okay, so that's a calculated value. We've got a yield strength that's specified, and we've got an area that's given to us. Pull everywhere question. We just calculated a value. How certain are we that the strength is actually going to be 875 kilonewtons? And what might cause the measured strength, if we were to take those 2 double angles, or take 20 sets of those double angles, pull them apart, what might cause the measured strength of those double angles to be different than the value that we just calculated? Take a few minutes, or not a few minutes, a few seconds, talk to the person next to you. If you have a friend at home who doesn't want to come to class, you can call them if you want. Take 30 seconds or so, talk about it. What's going to cause the measured strength of this double angle to be different than 875 kilonewtons? And I'm perfectly okay with not being able to hear my own thoughts here. You can yell, you can talk as loud as you want. Okay, the words seem to be more or less populating into the space here. Some good conversation that I'm sad to have to interrupt. I see some words like defects or imperfect. Imperfect is actually that's probably one of the better words to describe some of the variability in structural steel. We can never make anything perfect, right? You say, I'm going to roll a 1/2-inch plate. You're like, okay, roll me a plate to exactly 12.7 millimeters, and they're going to do it. It's going to do whatever. And then you're going to take a piece of, a pair of calipers, and it's going to be like, it's actually 12.66 millimeters. You didn't roll it perfect, right? You can never roll it perfect. There's always going to be some variability in the geometry due to the way that the crystal structures work, the properties, some stuff with cold working. the stress or the strength of the steel might differ. I'm telling this mill manufacturer I need 350W steel, which has to have a strength of 350 MPa. But if I take their steel and I cut it up into little coupons and test them all, I'm going to get 340, 360, 355, 380. The strength depends on lots of things that we can control relatively well, but it can't be perfect. We can never have exactly 350 MPa. We can never have exactly half an inch. And there are other things like the accuracy of the equation that we're using. AFY is pretty good. If you know the area and you know the yield strength, it has to be AFY. But there are other equations that are empirical in nature, which means you do a bunch of testing, you do some kind of best fit curve, and the equation has a certain amount of professional accuracy, we call it. Okay, so some of the terms I'm going to use to describe these things include bias and variability. What bias is it's the ratio of the mean measurement. For example, you break a bunch of steel coupons and you say the average is 380. You ask for a 350W steel, which has a strength of 350. And I think I used a slightly different number here. Let's say it's 368. You measure a bunch of coupons, on average it's 368, and I didn't change that number here, 368. The bias is the average of the mean to the nominal or specified amount, which in our case here would be 368 divided by the specified 350. It means on average, the steel is 5% stronger than the nominal value. Okay, so on average, the steel will be about 5% stronger if this was the average of the coupon test that we did. The variability is it's also called the coefficient of variation, but you'll usually see it called variability. It's the ratio of the standard deviation of the measurements. You can do that in statistics, divided by the average. Okay, so for example, if you did a bunch of coupon tests, and again, for some reason, didn't change that, 37. Get rid of that, 37. If you did a bunch of coupon tests, average was 368, standard deviation was 37, 37 divided by 368 it's about 0.1. Okay, so it's a measure of the spread and the uncertainty in the data. For the most part, structural steel has a pretty tight standard deviation, which means the standard deviation is going to be small relative to the mean. There are some other things like geometry. For example, how sure are we that the area is going to be exactly 2,500 millimeters squared? I don't know. Might have a small tolerance on it. And then there's the professional accuracy of the equation. For example, AFY. Now, AFY is what we would call a perfect equation. It's exactly right. If you know A and FY, it's exactly right. And so for that reason, we usually say that the bias for AFY is 1 and the variability is 0. You just can't have any different answer. But the geometry and material and other equations can have a bias and a variability. And basically, if you have a series of random normal variables that are independent of each other, the mean or the bias in the average test data compared to what you'd specify is just the multiplication of the bias in the data for these three components. And the variation or the coefficient of variation is going to be the square root of the sum of the squared values for the variability in those three terms. For example, in the 80s, and people still do this, these folks wrote a paper. They went and they measured flange widths, section depths, web thicknesses, flange thicknesses, and then they calculated the cross-sectional area and the moment of inertia for a bunch of wide flange shapes. Imagine how fun that is. You go down to Ocean Steel and just get calipers and measure all their W shapes and compare them to what they're supposed to be. Well, they did that and they got a bunch of statistics and they said, well, on average, the flange width is 0.5% higher than it should be. On average, the section depth is exactly what it should be. For the most part, what the measurements were a little bit more than what they should have been. And if you look at the variation or the variability in the data, it's very low. These manufacturers can roll things to 0.5% plus or minus 0.06%. So that's a pretty good, like 0.06 of the 0.5%. So that tells us that there's not a lot of variability in the geometry, but there is some. And so if we look at cross-sectional area, for example, we just use that to estimate the yield strength of the double angle sections. On average, we expect the area to maybe be 2% bigger than the 2,500, but there's some variation. There's a variability of about 0.012 relative to that area. If we have the strength, and we'll focus on yield stress here, on average, the measured values are slightly higher than the specified values. Again, pretty low variation, but higher than there would be associated with the geometry of the cross-section. And so if we took the area, for example, if we use the statistics that these researchers gave us, and we use the statistics for the yield stress that Galambos gave us from his research in 1977, what we can do is we can estimate what if we take the geometric bias and variation, the material bias and variability, and then because we're using AFY, which is quote unquote a perfect equation, we'll talk more about that later on in the course, we can calculate the total bias that we expect in our resistance estimates. We expect on average the resistance to be 7% higher than what we calculated, but there's a variability around that. So it could be higher or it could be lower. So on average, it's higher, but there's some variability. I'm curious, how could we determine the probability that we overestimated the strength by calculating it to be 875 kilonewtons? First of all, is it good or bad that we overestimate a resistance? Bad. If we're overestimating a strength, that means it's actually going to be weaker. That's not good. So if we said the strength's going to be this and it's weaker, there's more likely it's going to fail. And we'll talk about that more later. So we don't want to overestimate the resistance. How could we determine what the probability is that we just overestimated the resistance by doing AFY? Puts you in the uncomfortable position of having to think back to statistics, right? 2593. Let me prompt maybe a little bit of a thought here. If we know what the bias is in the resistance, then we can calculate on average what we'd expect the resistance to be for that pair of double angles. And if we know the variability, we know the average, we can estimate what we expect the standard deviation in the strength to be. And if we assume it's normally distributed, the strength as a random normal variable, we can plot the probability distribution curve. Right? So because the mean is higher than the estimate, the mean's somewhere out here, that means on average it's going to be higher, but sometimes it's going to be smaller. How do we determine the probability that we've underestimated or overestimated the strength using 875? What kind of problem is this from statistics? So it's a normal distribution problem for sure. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V. P tables, and it corresponds to a specific letter that comes at the end of the alphabet that I'd eventually get to. Z score, right? When you want to know the probability, left tail probability of a normal distribution, you figured out the Z score, and you went to the tables and you said probability. The probability is this area. This area tells me how often I will overestimate the strength if I use the value AFY. Okay, so I can calculate the Z score. That's just the estimated value or the given value minus the mean divided by the standard deviation. I get minus 0.65. And if I go to a stats textbook or use Excel or MATLAB, on average, I am going to overestimate the strength, right? The probability that the resistance will be less than what I've estimated is 26.5%. So 1 in 4 times, I'm going to overestimate the strength using AFY, using those statistics. What does that tell you about what we should be considering or what we should be thinking about if we were to, for example, try and estimate the yield strength of a member of a truss, for example, in tension? Should I be using always just the estimated value? Are you good with 1 in 4 overestimate? No, we've got to do something about that, right? We'll come back to that later on in the course, but you need some context for what's going on here. We calculate a value using nominal strength, nominal material geometric properties, and an equation that's given to us. There is a distribution of possible answers. We're getting one possible answer, and there's a probability we're underestimating, there's a probability we're overestimating. We want the probability that we're overestimating to be as low as possible. We'll come back to that in lecture 10 when we talk about loads. I've introduced the variability and bias in the strength of steel. We'll talk about the variability and bias in loads. And really what we want to do is we don't want to overestimate the strength at the same time that we underestimate the loads. Okay, and we'll come back to that idea in lecture 10. Okay, so now you should be able to identify some of those common shapes, pass some of them around, and tell me what some of them are used for, discuss the different grades, Canadian, American, and select the appropriate material properties. And what I mean by that is FY and FU for a given grade, and describe the bias and variability and the properties of structural steel shapes. This stuff you have to know because you're going to have to apply this. This you should know, but other than the quiz, I'm probably not going to ask you to like estimate probabilities on an exam or on an assignment, for example. I'll get you to do that on the quiz just because why not? Practice it once, you got a million tries. Otherwise, that's all we're going to be covering today. Does anyone have any questions about these 3 learning objectives or any of the material that we covered this morning? Great, have a great weekend, and I'll see everybody Monday morning.